So I want to start with a recap of the motivation and also something more which I want to mention in case I don't have time at the end. So first I was writing here, so as I told you last time, this is the story I want to tell you, which is how to compute gravitational entropy from the path integral. And this is based on notes from a course by Don Marolf at the University of Santa Barbara. And is also the material of a review I'm writing with David Grabowski and Zhencheng Wang, which will be out soon, hopefully. So this story about entropy from the path integral, which is something on which we are collecting more and more results in the past few years. So the last part is a very recent story. It actually started with a computation by Gibbons and Hawking for entropy from the Euclidean path integral. And this is what we have seen last time. So last time we first showed that to compute something like, actually to compute exactly the trace of the operator e to the minus beta h for a standard quantum system, we can perform a path integral along a closed circle. And then we generalize this to gravity. So based on this analogy with standard quantum mechanics, the fact that in gravity the Hamiltonian is a boundary term, and the fact that a gravitational path integral should in principle sum over all possible geometries and topologies compatible with the boundary conditions of your problem, we wrote this guess. So we said, okay, something like a partition function for gravity can be given by a path integral with some boundary conditions which are basically the same as for a standard quantum system. So you have a closed circle, which is the periodic Euclidean time, and then some boundary of space. And so this was our guess, and then we computed for the case in which these, so using the saddle point approximation, so approximating the full path integral with just the contribution from a solution of the equation of motion, we show that when we take the Schwarzschild black hole, the Euclidean version of the Schwarzschild black hole, using this guess, we indeed recover the Bekenstein-Hawking entropy. So this was a supporting evidence for this guess to compute a partition function in gravity. Today what I want to show is the two further steps. So one is by Lekovits and Maldacena, is a result of 2013, in which they did the same, but in a case in which you don't have time translation symmetry on the boundary. So this time symmetry is what gives you the trace of the equilibrium state. So in this case, you have an equilibrium partition function. So in particular, you are computing the trace of a density matrix, which is the Gibbs state, e to the minus beta h. Now, if you want the density matrix, a generic density matrix, not an equilibrium state, then how this story generalizes? Well, what Lekovits and Maldacena showed is that there is a sense in which you can set up the right boundary conditions to compute something like the trace of a generic state in gravity, and using the Euclidean path integral and the saddle point approximation. So we will see that there is we can construct a solution that computes this quantity. And the last step that I want to show today is how this story is then applied to the evaporating black hole. And in this case, so from here we get as entropy, well, I'm not going to write it, but the area over 4G. When we apply this Lekovits-Maldacena construction to the evaporating black hole, we get what is called the generalized entropy, in which you have the Bekenstein-Hawking contribution, so the area of the horizon over 4G, and then some quantum corrections which are given by the entropy of the quantum field theory. Oops. What did I do? I
don't know.
Ah, it's not my fault.
No, it's internet.
Non mi dire che la devo riscrivere tutta, ti prego. No. Ma prima ha funzionato e c'era ancora?
Lavagna esistente. No, fai un nuovo lavagna. No, ma voleva le cose per... proprio... L'ho fatto e ha funzionato. We lost information. Yes.
No, prima ha fatto nuova lavagna e
gliela dà?
Sì. Non so perché.
Usa classica.
Ok.
No.
No, ok. Well, it's gone. No, but I was starting again. But okay. Just, yes. You're right, just because I... Yeah. So we had Gibbons-Hawking. We had the Lekovitz-Maldacena generalization, in which there is no time symmetry. And then we have the island formula. Okay, yeah. And I was saying that here, as we are going to see, we have a contribution from the area and a contribution from the quantum field theory. Now, in particular, so so from the Lekovitz-Maldacena construction, we first get an entropy which is called a formula for the entropy, which is called the Ryuta-Kayanagi formula, in which we recover the area of a certain extremal surface, which I'm going to call gamma, over 4G. Then we will add the quantum corrections, and we'll see that in this case, we will get a quantum corrected version of the Ryuta-Kayanagi formula, which we have the area, and then we have the entropy of quantum field theory on a certain region. We'll see how the region is related to this extremal surface gamma. Now, the only thing I want to say now is the following. So, again, this is a story about entropy from the path integral. Now, the question is this just a story about the path integral, or we also need ADS-EFT, or more generally, an holographic dictionary between bulk and boundary, because this is the intuition we used to move from Gibbons-Hawking to the Lekovitz-Maldacena construction, which indeed is a story that makes full sense only in ADS-EFT. But we are going to see how it works, because it's the techniques that we will use for the evaporating black hole. So the question here is, so all these can indeed be computed just from a well-defined path integral with certain properties. And so this is an interesting question, because if this is true, then we can export these results to other approaches to quantum gravity with a well-defined path integral and check this against predictions of these other approaches. And a first step, which maybe I will talk about at the end if I have time, a first step we took in this direction, and is a paper from 2 years ago with Marolf, Shidong, and Zhencheng Wang. So in this work, what we did was to say, okay, let's assume that the path integral, so we don't know exactly how the path integral is realized, so on which geometries we are summing. So it's a sort of black box. And as a path integral should do, I fix some boundary conditions for this, and then I get some number. So we didn't specify what are exactly what is the exact realization of this path integral. We just listed some properties this path integral needs to satisfy. There are 5 properties. I won't write them, but are some very natural requests for a path integral. So we require it to be finite, to be real, to be reflection symmetric, because we want a path integral which is symmetric to compute the norm of a state. We ask it to be continuous, and finally, so maybe I will write them because otherwise it's confusing. So it's reality, finiteness. Then we ask it to be reflection positive for this property that it should give a well-defined inner product, basically. Then we require continuity, which is another very natural request. And the last property is factorization. This has something to do with wormholes. So we require that if we compute the path integral with where your space-time, the asymptotic space-time boundaries has disconnected components, the path integral factorizes. So this is assumption about wormholes. It's not crucial for what we are going to discuss, but the important thing is that what we showed is that if we have a well-defined path integral with these properties, then you can derive this Ryuta-Kayanagi formula, which is the first step, as I said, to move for the evaporating black hole scenario. This island formula is a quantum-corrected version of the Ryuta-Kayanagi formula. And so what we did in particular, if you recall at the beginning, when we talked about gravitational entropy, we were saying entropy in gravity is tricky because when you talk about entropy, you want to talk about entropy of some observables. But in gravity, observables are non-local, so it's tricky to construct local observables and have an entropy defined in terms of that. And it's also tricky to have an Hilbert space interpretation because in gravity, the Hilbert space does not factorize. And what we did was for a gravitational system with 2 disconnected asymptotic regions. This is just a cartoon, but what we did was to construct observables with the path integral. So we constructed both an algebra of observables and a Hilbert space on which this algebra was acting. And this based only on these 5 actions, 5 properties. And why this is interesting, because if we can generalize this was in the Euclidean case. If we can generalize this to the Lorentzian case, adding quantum corrections and so on, then we might have a derivation of the island formula just from some properties of the path integral. And the last thing I want to say about the motivation and the introduction is that, so characterizing a path integral through these properties is something that does not constrain the UV bulk structure. So well, I will write in short like this, but the point is that these are very general properties which are not saying anything about the degrees of freedom at the Planck scale of our gravitational theory. So when you want to compare these to other approaches to quantum gravity in which you have a path integral, a specific realization of your path integral, then there is the problem of like comparing two very different scenarios. So what I have in mind is in particular approaches like loop quantum gravity, group field theory, or more generally simplicial gravity. In which you do have a realization, this was Z for the path integral, in which you do have a realization of your path integral in terms of sum over some simplicial complexes with some coloring. In loop quantum gravity and group field theory, these are called spin foams. And this is the network dual to these simplicial geometries, and you have some, you sum over all possible coloring of this network. And so your path integral will be a sum over amplitudes for vertices and faces, something like this. You have an amplitude for the vertex. You combine the amplitudes for this network, and you have a realization of the path integral. So, and the question if these path integral, these results that seem to rely only on the path integral work for specific realizations like this is particularly interesting because in the case of the evaporating black hole, the predictions are very different. Now, last time I mentioned the page curve. So when we consider the Hawking radiation, we compute the entropy. And the process seems to be non-unitary, information seems to be lost. There are approaches, particularly loop quantum gravity, in which you don't even expect the page curve. The island formula is, in particular, as we will see, is something that allows you to obtain the page curve. There are approaches like loop quantum gravity in which you don't even expect it. So, in particular, you have the so-called remnant scenario. So there are actually several proposals. One of these is the so-called black to white hole transition, in which you have a space-time like this, you have your event horizon, and then there is a quantum gravity region on which we are ignorant about. But the idea is that your black hole horizon does a sort of tunneling into white hole horizon. And so information actually goes out through the white hole. This is the white hole. And this is the black hole. So in this remnant scenario, there is not even a page curve. So there is, as you can see, there is a conflict between these two computations of entropy. Okay, this was a very long motivation. But today we are actually just continuing the story about entropy from the path integral, first with Leibowitz-Maldacini and then with the evaporating black hole case with the island formula. So yeah, here we say no UV bulk structure. Instead here you have specific ultraviolet structures. Are there questions about this part? No. Okay. So okay, so we are interested in the entropy. So let me remind you the von Neumann entropy. Sorry, I'm already. Okay, so we have a certain density matrix. We want to compute the entropy, and this is the trace of rho log rho. Now, usually this is very difficult to compute because of the logarithm. A quantity that is much easier to compute is the trace of rho instead of the trace of the logarithm. And we are using the fact that we prefer to compute this quantity than that quantity to actually compute the von Neumann entropy through the so-called replica trick, which is saying that the von Neumann entropy so first let me define the Renyi entropy, which is the following, is that you take n copies of your system, or actually you take, you exponentiate your density matrix to some integer number n. Then you take the trace, you divide by n minus 1, and, sorry, there is a logarithm here. So this is the Renyi entropy of order n. And the replica trick consists in the fact that you can define the von Neumann entropy for your density matrix as the limit for the number n that goes to 1 of this n Renyi entropy. Okay, yeah, this is the replica trick. Okay, so the object of interest for us is this quantity here, the trace of the density matrix to some power n. This is what we want to compute. As I mentioned at the beginning, last time we saw that we can compute something like the trace of e to the minus beta h in gravity by using boundary conditions, a circle with time translation symmetry, and perform a path integral which has as boundary this circle with the symmetry which is having a Killing vector field on your boundary. We are going to see now the Lakovics-Maldacena generalization, in which instead we compute something like the trace of a generic density matrix, and in particular then this generalization to the density matrix to some exponent. So this quotation mark I'm putting here is because I want to talk about this beyond the DSCFT. If you are working in a DSCFT, then everything is well defined. There is no need for quotation mark. You are really, because you use the dictionary, so you are really computing the trace of some density matrix. Okay. Okay. So let's make this concrete. So we are studying a system that we saw also last time, which is a gravity in a box system. So in particular, we have a gravitational system, is some bulk space-time, so 4D bulk space-time M, and then we have a three-dimensional boundary, the boundary of our box, which will be some R, which is for the time direction, times some sphere. So in particular in this picture, the sphere, the boundary sphere will be this circle here. Okay. So I'm actually drawing S2 as a S1 to be, so this is actually S2. Okay, so this is our system, our gravitational system. And in particular, so this is a Cauchy, the boundary of a Cauchy surface. The Cauchy surface is the disk. On the boundary of this Cauchy surface, let's take a region R. So we split this surface into two components, R and the complement. And we want to compute the trace of the density matrix reduced to this region R to some power n, because of what I told you before, that we are interested in computing the Rényi entropy and so the von Neumann entropy. Now, again, if you recall what we did last time, we said, okay, for a standard quantum system, we have, for the trace of e to the minus beta h, we have the path integral along S1. What we do for gravity, we use that path integral as boundary conditions of our gravitational path integral. So the guess here is that the boundary conditions, so actually the boundary manifold, we need to use to compute this quantity. So to compute this quantity in gravity, are given by the path integral that compute the analog quantity in a non-gravitational system. So the path integral for the analog in a non-gravitational system so in a non-gravitational theory on the boundary of our box. So this is the intuition. We need to fix some boundary conditions to compute this quantity, and to do that we look at which path integral computes the analog quantity in a non-gravitational theory, which lives on the boundary of our box. So this means that to compute that quantity, we first need to understand the entropy for a quantum field theory on the boundary of our box, so which is the time direction times S2. Okay, and we are going to do this like with pictures. So first I want to remark something that maybe is clear for you, but might not be so obvious. So in the first lecture we saw that we can compute the transition amplitude between two states using a path integral. And so in particular, when we fix the initial and final state in this path integral, we are summing over all configurations which have this as a starting point and this as a final point. Now, something you can do is to not specify the final state. So imagine that here I was integrating in a very informal way between some initial and some final boundary conditions. Now, if I don't specify the final boundary conditions, I can actually write a state as a path integral like this. Now, this is a formal way of writing my state, but it's something we are going to use again and again, so it's important that this is clear. So in particular, what is the state that I formally write as a path integral? Is a state such that if I specify the final boundary condition for my path integral, then I get the amplitude, or if you want, the wave function of my state. Okay? So this is to motivate the fact that I'm going to write state by using the path integral. So we are considering states as prepared by a path integral. So we need to understand entropy for quantum field theory on this manifold here. So, okay, let's say this is our S2. I'm writing just as a line for simplicity. And so this is my manifold. This is the time direction going up. Now this is my Cauchy surface, the red one. Now I want to define a state on this Cauchy surface. I can write this state as a path integral. So with this picture, what I actually mean is a path integral preparing a state psi. Now we want to construct a density matrix. So here we have the cat. We need to construct the bra. For the bra, we just mirror the image of this. So let me do this. This way I'm constructing the bra. Okay. Now on our Cauchy surface, we said that we want to compute the entropy of a subregion R. So we want to split our Cauchy surface in two. There is a region R, which is the one in which we want to compute the entropy, and then there is the complement. So we have the same on the bra. We have the region R and the complement. So now I wrote the density matrix of the full system. So the density matrix which is given by the projector, the bra, and the cat psi. But I want to compute the density matrix associated just to region R. So I need to trace the complement. How do we trace the complement? In terms of our space-time manifold, we just glue the part we want to trace out together. And see, this is something we saw in the first lecture when we were doing the path integral on the line, and to compute the trace, we just close the loop. We are doing the same here. So if I want to trace out this complement region R bar, I glue this piece together. With this picture, I computed the density matrix for R. But what I wanted to compute is actually the trace of rho to some exponent n. So let's take n equal to 2. So we need another copy of this picture. So I have, again, the complement. I actually use the green for this region R. I glue the complement together as I did before. And now with this picture here, what I have is the trace of this density matrix square. Okay? Now what we want to do, we want to compute the trace of this object. So we need to trace this. And how I compute the final trace, I glue the remaining part. But now I need to glue the first copy to the second copy, like this here. And then glue this, the bra of the second copy to the cat of the first copy. This is the manifold that is computing this trace of rho squared. And now look what happened at this point here, which is the boundary between R and R bar. So it's the boundary of the region of which I want to compute the entropy. What happened is that I get a conical singularity, because if we start, so let's start from here and do a pi rotation. I do a pi rotation, and I get, since this is glued to this, I go back here. Then I do another pi rotation, I end up here. Then I do another pi rotation, I end up here. this is glued to this one, so another pi rotation, and I'm finally back here, because this is glued to this. So what happened is that I need the 4 pi rotation to go around the splitting surface. So when I write the manifold that is computing this quantity, I get a conical singularity, because I need this 4 pi, a conical singularity to go around the splitting surface. Okay, so this is the trace of rho squared, which is e to the minus the second Rayleigh entropy. Now, according to, so this is in quantum field theory. And let me call this manifold, this boundary manifold, computing this as B2. Now, following what we said many times now, that we want to use as boundary condition for the gravitational path integral what computes the analog quantity for a non-gravitational system on the boundary, so in this case the quantum field theory on the boundary. So the point is that we should use this as boundary. If you want to compute this quantity in gravity, we should use this manifold as boundary conditions. So just as a cartoon, what I'm going to do now is to use this as boundary for a big path integral in gravity, where I sum over all possible geometries and topologies compatible with this boundary manifold. Note something, that this boundary manifold here has a symmetry, has a replica symmetry, because I take 2 copies. So we have a replica symmetry here. Okay. So now we do this big path integral with these boundary conditions, and we are going to look for saddles for this gravitational path integral. So now my saddle would be some 4-dimensional manifold. In this case, M2, because I'm doing everything for 2 copies. Okay, so this saddle, this manifold, is such that the boundary is this boundary B here. So this is what we are going to do, and using the saddle point approximation, then the action computed on this saddle should give me this quantity I was looking for in gravity. Okay? Questions on this? No.
Very naive question. Why is it easier from algebraic point of view to calculate the limit for n to 1 instead of calculating for only one system? Which is the vantage point from algebraic point of view?
So the advantage is that so for just n equal 1, you don't get the von Neumann entropy. The Rayleigh entropy.
Yeah.
So the advantage here is that in the von Neumann entropy, you need to compute the trace of a logarithm of the density matrix. With the replica trick, you can forget about the logarithm, because you have the trace of the density matrix.
Yeah.
Now, you take the limit for n that goes to 1, because for n equal to 1, the Rayleigh entropy diverges, because you have 1 over n minus 1. So the advantage of the replica trick is that you just need to compute the trace of a density matrix instead of the trace of the logarithm of a density matrix.
Okay. And one could say that there is something similar to the idea of Gibbs of making statistical mechanics with ensemble, or there is no analogy, or there is a partial analogy?
No, there is indeed. We are actually going to use that because you can actually take so here you are considering the density matrix to some exponent n, but I can equivalently taking just the tensor product of n equal system and performing the trace. So if your full state is a tensor product like this, then it's perfectly equivalent. We are going to see that something funny happens with gravity, so that these many copies are actually correlated. But I mean, there is a sense in which you are actually considering an ensemble and taking n copies of your system. Okay.
Took the topological dual or something, and then glue together the R region, like R regions. So, I mean, in what space does B2 live? So, like, it's not totally clear to me.
Oh, this is a
the topological aspect of that. So, like, what do you do?
Yeah, I was maybe too fast on this. So imagine we have a quantum field theory, and then I want to write a state. I integrate over my field. I have some action for my quantum field theory. And if my quantum field theory is living on a manifold like this, which is R times some sigma, and this is sigma, I can formally compute, like, for example, the vacuum state if I integrate over minus infinity here. But in general, formally, I can put some sources here, perform the path integral. I don't specify the final configuration, and I prepare a state. And what I mean by this is that if you actually tell me the final configuration here, so let me call it like phi tilde, and so I specified all boundary conditions for this case, so I have my path integral preparing the state psi, but I also tell you what is the configuration on the Cauchy surface. What I'm actually computing is this transition amplitude, so it's actually the wave function, if you want, like this. And now, when I glue things together, is because so imagine what is going on here. If you put, I can insert the resolution of the identity at a Cauchy surface. And the resolution of the identity will be like integrating over all possible field configuration with something like this, right? And when I insert this between two path integral, I put it one below the other but when I put this is equivalent, is like if I put the resolution of the identity and I integrate over, this is just, I can forget about it basically. I'm just gluing together two pieces.
Oh, okay.
So I put the resolution of the identity here, but it's equivalent to have the full manifold, okay. And I'm still integrating over all configurations.
Okay.
Yeah, so this is like a very condensed way of like writing things. It's because it's going to be easy to, I mean, instead of writing all the integrals. Okay, so, no, this is another Okay, so we are computing this quantity. Again, our path integral and the boundary conditions are the manifold of the other page. We use the saddle point approximation, and this will be the exponent of the action computed on some solution. This four-dimensional space-time manifold. And the boundary is this B2 of the other page. Just so that we remember it was something, this was glued to this, and then this was glued to this. Now this boundary, so now so this boundary, not the following, we said this boundary manifold has a conical singularity on the splitting surface between the region R, of which we want to compute the entropy, and the complement. So the boundary has a conical singularity, but the bulk is smooth because we want a solution of the Einstein equations. So the bulk must be smooth. So the assumption that Lekovits and Maldacena made was that the bulk, so since I have this replica symmetry on the boundary, the assumption is that the bulk solution preserves the symmetry. So now we have the following. Again, it's like a cartoon. So we have this circle, which is our boundary manifold, which has some replica symmetry. So we have all these segments which are equal to each other. Okay? And now we are assuming that the bulk preserves the same symmetry. So what we get is a sort of pizza in which all slices are equal to each other, okay? So the full bulk saddle is this Mn. What we can actually do, since we are assuming that the saddle preserves the symmetry, is to move to a quotient description which I'm going to call M tilde, N, in which we take the full saddle and we divide by the symmetry. So this means that we are actually focusing only on one slice of this, okay? So this is our new the manifold we are focusing on, just a slice of this. And now look what happens. Before we had the boundary conditions with a conical singularity, but the bulk was smooth. When we move to a quotient description, what happens is that the boundary condition, which is just the same as one copy, so the boundary of this M tilde is just the boundary of M1. So the boundary is smooth, but now the bulk has a conical singularity, which is the center of this disk, the surface which is invariant under replica symmetry. So we now, when we move to this quotient description, there is this swap. Now we have a conical singularity in the bulk, and the boundary is smooth. And this conical singularity, the strength of this conical singularity is related to the number of copies we consider. So in particular, we have a deficit angle, which is 2 pi 1 minus 1 over n. So we want to compute, we are using the saddle point approximation, so we need to compute the contribution there, the exponent of the action for this saddle. So, okay, so let me write again the boundary. Then we have all these slices, and we are focusing only on one. This is some tilde, n, while the full bulk saddle was just m. So we want to compute the action evaluated on this saddle, the full saddle. And now we can write this as n times some action for just one slice of this pizza. Okay? But now note the following, that when we write the full action as n times the some action for a single slice, this cannot actually be just the Einstein-Hilbert action. Why? Because the Einstein-Hilbert action is 1 over 16 pi g. Then we have the integral, the determinant of the metric, and the Ricci scalar. But we said that this slice has a conical singularity. So the Einstein-Hilbert action would actually see this conical singularity because the curvature is divergent there. And this is cannot happen because on this side we actually have the Einstein-Hilbert action for a smooth manifold. So there is no conical singularity on the left-hand side. So this action here cannot be just the Einstein-Hilbert action. And so how can we write the action for this slice? The action is going to be, so what we need to do is to consider just the Einstein-Hilbert action and then add a piece that compensates this divergence for the conical singularity. So we have the Einstein-Hilbert action evaluated on this slice, and then we add a piece that can cure this extra factor from the conical singularity that we don't want. And last time we briefly see that for a conical singularity what I get as a contribution is something proportional to the area of the conical singularity for this manifold over 4G. Okay. So we want to compute the Rayleigh entropy of order n. We need to compute this e to the minus the action for this manifold. Actually, so when I said I can prepare a state through the path integral, this is not a normalized state. So if I want to normalize the state, actually here, so when I compute the trace of some generic state which is not normalized, so let me write this n as for unnormalized. What I do is that I need to normalize it by dividing for a factor which is the trace of rho, which would be 1 if the state was normalized, to the n. So actually we are not just interested in e to the minus the action, but we need to add the saddle point contribution for this normalization factor here, which is n times, and then this is just the trace of one copy, so the action for the manifold for n equal to 1. So what we are actually looking for is the quantity e to the minus, and then we have the action for our saddle point minus n, and then we have the action for m1. Then I'm going to use this equation here, in which I write the action for the full saddle as n times the action for just one slice. So this is going to be n times this action I tilde for my slice. We are almost there. Okay, so let me also write again the von Neumann entropy is the limit for n that goes to 1 of the Renyi entropy of order n, and what we have just seen is that this is given by, there is actually n that I can, from here, I can actually take out this n, and I put it here. So I have the action for a single slice minus the action for the n equal 1 saddle. Now, from this you see, since I'm taking the n equal to 1, here I have the difference between the action for the saddle point with generic n and the saddle point with n equal 1, and I'm dividing by n minus 1. So this is just the derivative in n of my action, evaluated for the case n equals to 1. And now if you substitute here this expression of the action for the slice, in which you have this contribution for the area of the conical singularity, what you get, and maybe I should give you directly the result. Well, basically we need to do just the derivative well, let me, maybe I will write just one intermediate step. This is this, and then 1 minus 1 over n, and then the area for the conical singularity over 4g, everything evaluated for n equals to 1. And when you perform this derivative, well, this term is going to disappear because this is evaluated in the end for n equal 1, so this is just a stationary point for the action. Then we have, when we do the derivative of this term is going to be 0, because again we evaluated for n equal 1, so this parenthesis disappears. And so the only terms that survives this is this limit for n that goes to 1 of the area of a conical singularity for this slice over 4g. Okay, so let me just comment this formula, maybe then we do a 5 minutes break. So let me do just a quick recap. We want to compute the von Neumann entropy through this formula, the limit for n that goes to 1 of the Renyi entropy. And we fix these boundary conditions which have some replica symmetry. But then we said, okay, let's assume that the bulk also has a symmetry. So instead of looking for the full saddle, let's look at just one slice. So we look at just one slice and we write the full action as n times the action for a slice. Action that cannot be just Einstein-Hilbert, must be Einstein-Hilbert plus a term, which is this one, which cancels the conical singularity you get here, because the full action, since the bulk was smooth, the full action cannot have this conical singularity contribution. So by doing this and performing this limit for n that goes to 1, we find this result, that the von Neumann entropy is given by the area of a conical singularity. So when we perform the limit for n that goes to 1, we go back to looking at the original manifold. And so the question is, okay, we got the area of a conical singularity, so the area of a certain surface, but which surface is that? In the original, just n equal 1 copy, because, so in the end we are computing the entropy for our system, and we are interested in understanding which entropy is that on 1 copy, not on n copies. So to understand which entropy is that, look at the action this action here. Now this action here, you have the Einstein-Hilbert action, and then this term, which is like a source. This term here is like a source, which is for n that goes to 1 is weakly coupled to gravity. This is the Einstein-Hilbert action. And so you can understand this as a sort of back reaction on the gravitational system, a back reaction in which indeed you get, so because of this source you get a conical singularity. And also this is a sort of action for your source. And we know that when we want to compute the saddle point, we need to extremize the action. So the final surface must be a surface that extremizes this quantity, so that extremizes the area. So basically this is telling us what are the equation of motions for our surface. So what we get is that the right surface which I'm going to call gamma, direct surface in our original space-time manifold is the one that extremizes the area and with the condition of being anchored to the boundary of R. So our starting point was we wanted to compute this quantity here. And so we started with these boundary conditions with a splitting surface between R and R bar. And then we moved to this quotient description, we moved the conical singularity in the bulk. But in the original n equal 1 copy, the conical singularity is the splitting surface between R and R bar. So what we finally got is what is called the Ryuta-Kayanagi formula, which is telling that the von Neumann entropy for the region R is the area of some surface over 4G, and the surface gamma is the surface that extremizes the area and is anchored to the boundary of R. What we derived with this Lakovics-Maldacena construction is the so-called Ryuta-Kayanagi formula. So we started with the system, what we call the gravity in a box. So we have our system with a finite distance, And we considered on this slice, sigma, we consider a subregion of the boundary of sigma, we call R, and we ask what is the entropy associated to this region. And what we found is that thanks to this replica trick, and the fact that with the replica trick, when we do the replicas, we glue things together to perform the computation, we found this conical singularity on the splitting surface between R and the complement. Thanks to this splitting surface, this conical singularity, we recover a contribution which is the area of a certain surface gamma, which is, when we look at the computation with the many replicas, gamma is indeed this the surface here, which is invariant. This is the point which is invariant under the symmetry. And we found that with some motivation for this extra contribution in the action coming from this area of the conical singularity, we found that the correct surface in your original bulk space-time is a surface that is anchored to the boundary of R, so this point here, and which extremizes the area functional. An example to connect this to what we saw last time. Last time we considered the Kruskal extension of Schwarzschild. And we took so we moved to the Euclidean time. So let me take the time symmetric slice in the Lorentzian picture. Then we did a weak rotation. So we actually moved into imaginary time, which you can imagine be perpendicular to this plane, to the whiteboard, which is periodic. So the Euclidean picture of this is this one, right? This is so we got the so-called Euclidean cigar. This is periodic Euclidean time here, perpendicular to the whiteboard. This is the horizon, which is the tip of the cigar, okay? And so if we look at this slice, the blue slice is the blue slice here. And if you ask, we do the computation that we just did, but so now let's look at this asymptotic on the boundary of this foliation, of this Cauchy surface. Look at these two spheres. And you compute the entropy. What is the area that the surface that extremizes the area is indeed the horizon here. So you indeed find that this is now your gamma. So the entropy is the entropy of the horizon divided by 4G. Okay, something I wanted to do, but I will skip because otherwise we don't get to the island formula. So I want to move to the evaporating black hole. So the part I won't do, but you can ask me later if you are interested, is to add the quantum corrections to this. So this was the Ryuta-Kayanagi formula. This was formulated by Ryuta-Kayanagi 2006 in a DSEFT. Lekovitz and Maldacena did this replica computation in 2013. Then you can add quantum corrections. So instead of doing just the gravitational path integral, you do the path integral and you add the quantum field theory. So when you sum over geometries, you also sum over the quantum field theory configurations. And what you find is that you need to add to this term a correction which is the von Neumann entropy of the quantum field theory on some region sigma. This is a bad notation because I call the sigma this. No, in this case, sigma is this region here, which is bounded by R and gamma. Okay? And this is called, the full formula is called the generalized entropy. Generalized entropy for a surface gamma. And this was conjectured by Netta Engelhardt and Aaron Wall, and then was proved through this replica computation. Okay. Now we move to the black hole. There would be many steps to go from this to the evaporating black hole pictures. Many steps. The main one is that this story was actually in the Euclidean case. We should move to the Lorentzian case. When you go to the Lorentzian, in addition to the conical singularity we found, we still find a conical singularity, but it's even worse because then you have this causal structure here. So something funny happens with the causal structure of your space-time when you do this path, when you cut and glue stuff together like that. So the Lorentzian version is called HRT. So this was the Euclidean version. The Lorentzian version is called HRT from Ubeni, Rangamani, and Takayanagi, which I'm not going to review. The logic is the same, so we will just move to the black hole case. Okay, so let's go to the black hole. Let me briefly mention, let's start with the stationary black hole. So let's imagine that we create the black hole by collapsing some matter. And then we have also a quantum field theory that we put here in the vacuum state. You have some Hawking radiation escaping to infinity. Now let's imagine that we collect all this radiation. For simplicity, let's imagine that we put it in a box where gravity is not dynamical. Okay, so we have all this radiation. We collect the radiation in the box. So here we start from a pure state. So the initial entropy is 0. If this process, the entropy of the box, also the initial entropy of the box, you assume that is 0. So if this full process is a unitary process, okay, then you expect the entropy of the full system to be 0. But the system is pure, so if you compute the entropy, so let me call U the retarded time. So imagine that here you are computing the entropy of the radiation for a portion of the future null infinity up to retarded time U. Okay, if the whole system is in a pure state, then the entropy of the gravitational system at each retarded time must be equal to the entropy of the box. So the entropy, you keep collecting this radiation, so the entropy of the box increases and the entropy of the gravitational system increases. But so the problem here is the following. So you have the entropy of the radiation, which keeps increasing like this. So this is a function of the retarded time. But the Bekenstein-Hawking entropy, which is in terms of the area of the horizon, is decreasing like this. So there is a point, which is called the Page time, in which the entropy of the radiation is equal to the Bekenstein-Hawking entropy. And what is the tension here? The problem here is that at some point you get that the Bekenstein-Hawking entropy is less than the radiation entropy. And this cannot happen if you assume that the Bekenstein-Hawking entropy, according to black hole thermodynamics, behaves as a density of state. Well, e to the minus the density of states. So in other terms, according to black hole thermodynamics, it seems that the Bekenstein-Hawking entropy is telling you how many degrees of freedom are in the black hole. And you cannot entangle a system with another system with more entanglement than the amount of degrees of freedom of your system. So it's not possible, if the Bekenstein-Hawking entropy is indeed the density of states for the black hole, it's not possible that the entanglement entropy exceeds this quantity. And so this is the reason why Page conjecture that there should be some corrections to this process so that the actual curve for the entropy is this one, so is the minimum of the two curves. Okay, so Page 1993 said, okay, there should be some corrections such that the entropy follows this curve. Okay, so let's see what happens when the black hole evaporates. So when you have a black hole, you actually have some negative energy flux, which causes the space-time to back-react. And so the diagram actually looks like this. So here you have the Hawking radiation. Here, here you actually don't really know what happens because it's a quantum gravity region, but what we are interested in is the entropy for this region here, which is the Scri plus, the future infinity up to retarded time u. So we are interested in computing the entropy for the radiation in this region here. Now, so we want to set up a computation for this with the path integral. So what we do, in particular, as we did before, we actually prepare this state through the path integral. So I as before, I have some, I didn't put it here, some matter falling to create the black hole, and some quantum field theory in the vacuum. So these are the boundary conditions. These ones are the boundary conditions in the past, which I set in order to prepare my state. So I set these boundary conditions in the past, and then I let the path integral to evolve these conditions and prepare a state at the future infinity. So in particular, this is preparing some state, psi. But as before, we also want the bra. So I take another copy of this. And what I said, what we want to do is to actually look at the state on this portion here up to retarded time u. And so we can trace out the interior region, because I only want the reduced state on this pink region. And we want to trace out this. So okay, going to be like this. So the idea is that I'm completely ignorant about what is going on in the future of this Cauchy surface, because I'm tracing out these two, and as we did before, when I trace out, I need to sew together these two pieces. And note that as, I mean, so this is computing some density matrix for this region here, the future infinity up to retarded time. If I was putting some configuration alpha and beta here, the path integral filling these boundary conditions would be computing this expectation value. Is this point clear? Because this is very important. That we are preparing the state using the path integral, and we set some boundary conditions for our computation. If we wanted to compute this quantity, then the right boundary conditions would be this one with some configuration alpha and beta. And then the question would be, so these are my boundary conditions, then how the path integral is going to fill them, because again, the path integral is a machine in which I give boundary conditions and then I sum over all geometries and topologies inside. And so there are several things that can happen in this dynamics which is controlled by the path integral. In particular, there can be many saddle points that contribute. One saddle point is the one computed by Hawking, is the perturbative saddle. But what we are going to see is that there are other saddles which can arise in this computation, which are different from the Hawking one, which are non-perturbative. But this is something that appears when we set up a replica computation. So let's set up the boundary conditions. Again, this is important, that what we set is the boundary conditions, and then we let the path integral in the bulk to determine what happens. So I go up to this, but then it should be bigger. So this is the cat and the bra for one copy. So this is copy 1. Let me remind you I have the vacuum in the past. And this is the region we are interested in up to retarded time, u. But then I take another copy. Like this, and yeah, and again up to retarded time u. So we trace out the end of the evaporation. So there is an event horizon forming here, but then the end of the evaporation is actually in the future of the Cauchy surface that from which we are tracing out. So an important point about this island formula, the replica computation, is that there is no assumption of what is going on at the end of the evaporation, because we are still far from that quantum gravity region. So if I want to compute, so we saw before that the interesting quantity was to like the trace, so this is copy 2. The interesting quantity was the trace of rho squared. So a very like a standard way to trace out the complement of like the region of interest, which is the pink one, would be to trace out this region here, to trace out this region here, then with this picture I'm computing rho squared, and then to compute the final trace I just glue these pink regions together. Now the calculation we want to, so first, so here when we trace out the complement of the region we are interested in, this is a sort of state of ignorance. So we are saying, okay, we don't know what happens in this complement region. But the path integral, which is integrating over all possible configurations, in principle should sum over all possibilities for the interior. So look at the following. So if we set up these boundary conditions for the path integral, there is one saddle, which is the Hawking one, in which indeed you just have these two perturbative spacetimes. So imagine that these are just two copies of the Hawking computation, and this is the standard perturbative saddle. But in this blue part that we are tracing out, we can actually consider less obvious things. So, because again, this is like a statement of ignorance. So we don't know. The path integral is just tracing out these blue parts. So among the possible ways in which you can glue these parts together and trace them out, there is something that you can do. So instead of so the normal gluing that was like the cat and the bra of the same copy, you can actually split this part in two. And the same on the other side. This is the interior. Again, this is the part the path integral is summing over. And so you have you put a splitting surface here, which is this point. And there is a part which is this blue one, that, as before, you are gluing the cat and the bra of the same copy. But then what you can do is, and I messed up the colors. So I wanted to do actually this to this and this to this. Yeah. So instead of glue, so this part, the blue part is just as before, okay? Cat and bra of the same copy. What you can do, well, if you add this splitting surface, the green point, is to instead add this extra part, the orange one, the bra of copy 1 to the cat of copy 2, and the same here. You glue the cat of copy 1 to the bra of copy 2. This is what is called a wormhole, because it's connecting asymptotic regions of different spacetimes. So what is the idea? Is that so the boundary conditions we put for our path integral were conditions in the past, because these were the past boundary conditions to prepare the states. And then we are interested in the final boundary conditions, because it's the pink ones, which are the one giving us the output state. And everything else must be traced over. And in the possible ways in which you traced over, there is a simple way, which is the Hawking saddle, and there is this other way in which you actually include a splitting surface, and there is a part that you trace between different copies. And so you have these wormholes contributions. And this part is called the island, the part internal to the splitting surface. How much time do I have? Yeah. 5 minutes. Okay. So let's see, because it's now imagine that. So we talked about the Rayleigh entropy, the way in which we can compute the Rayleigh entropy through the replica trick as a limit of the von Neumann entropy as a limit of Rayleigh entropy. Now, a way in which you can compute, like operationally, the Rayleigh entropy is by computing the so-called swap entropy. So the swap operator is if you have a Hilbert space, which is the tensor product of two Hilbert spaces, the swap entropy, the swap operator is an operator that just swaps the cat and the bra of your system. And you can define the swap entropy. Let's consider order 2. So basically you are taking the expectation value of this swap operator on your density matrix. And you define the swap entropy like this. Now, if your system is the tensor, if the density matrix you are considering is the tensor product of two density matrices, so in other terms you have two copies without correlations, then the swap entropy is just equivalent to the Rayleigh entropy. And indeed, this is a way in which you can operationally compute the Rayleigh entropy. It's going to be different if the two copies are actually correlated. So you can set up the boundary conditions to compute the swap entropy, and then in particular compute the von Neumann swap entropy as a limit for n that goes to 1 of this swap entropy for a generic n. So what we are, and this is the density matrix for a certain number of copies, but I shouldn't really say copies because in principle, I mean, this is if this is true, then the swap entropy and the Rayleigh entropies are equivalent, but we are not assuming this. So we are just setting up computation, the boundary conditions to compute the swap entropy and see what the path integral is telling us about the resulting density matrix. So is a way to copy this? No, to the next. So I'll try and be quick. So I want to compute the entropy, the swap entropy. For this density matrix, for the portion of the future infinity up to some retarded time u. So in particular, to compute this, I need to compute the trace of this swap operator the expectation value of this swapping operator. Then again, so what I'm doing here is now the difference when I introduce this swap operator is that I actually glue this part to this part and this part to this part. And these are the boundary conditions to compute this. And then once more, with the path integral, I sum over all possibility in the interiors. And as I said before, there is something I can do here, which is tracing out the interior by adding this splitting surface. And then glue things in this way, so having these wormhole contributions. So this part is just glued in an ordinary way, so with the same copy. But then there is the internal part, the island, that I can actually compute in a way of having wormholes. Okay? We are almost there. So this is a splitting surface. Now, this is the green point is our splitting surface. Now, if we do the computations we did before, which is analogous to the one we did last time, what we find? We find that when we estimate the action, we find the generalized entropy for the region gamma, which is the area of gamma over 4G And then the quantum corrections, which we didn't compute, but and if you remember, we said that the quantum corrections are the quantum field theory contribution on a surface, which is the surface between the splitting surface and the boundary. And now this is the last piece of information we need. So look at this region here. This is a Cauchy surface, right? So the entropy, now here I want sigma out, which is this pink region here. Is the region which is between the splitting surface and the boundary. But since this is a Cauchy surface, the quantum field theory on sigma out is just the quantum field, the entropy of the quantum field theory on the orange and the red part together, because on this Cauchy surface I have a pure state, so the two entropies must be the same. So I have the quantum field theory of the island union the region on Scri plus we are looking at. So this is the area of gamma over 4G plus the von Neumann entropy for the quantum field theory on the island union the region Scri plus. Okay, we are there. So what are the saddle points? There is one saddle point because, so we said that this gamma must be a quantum extremal surface. So in our computation, we should look for extremal surfaces. Classically, there are no extremal surfaces because, I mean, you can extremize the area in the outgoing direction, but in the ingoing direction, the black hole is shrinking. So there is no extremal point surface. But when you add these quantum corrections, you actually find that, so here I trace out this picture is not very clear, but if we go back to this one, when the black hole is evaporating, I have the event horizon, which is a null surface, but then I have an apparent horizon, which is defined by the null expansion of the zero expansion of the null rays, which is a time-like surface. Now I'm a bit exaggerating, but this is the apparent horizon. And if you do the computation, what you find is that there is a quantum extremal surface, so this green point, which is the intersection of the apparent horizon and such that, so because when we trace out, we are tracing out like this, and the position of the quantum extremal surface is such that this portion here is null. So equivalently, you can find the quantum extremal surface as the intersection between a null ray from the retarded time u and the apparent horizon. Now the picture is very bad, but this is a null. So there is a quantum extremal surface. So there is a saddle point with a non-trivial gamma. So in the end, we find there is a saddle in which this splitting surface, because you can go back to the Hawking computation and without these wormholes, if you move the island in this direction, so that in the end there is no island, there is no splitting surface, so the island is zero. There are no wormhole contribution, you are back to the perturbative space-time. So there is a case in which the island, the quantum extremal surface is null. And so in this case, you are left, so this area contribution is zero, because the quantum extremal surface is null. And so the entropy is just the entropy of the quantum field theory. So look here, this is 0 because we said no island. So you are left with the entropy of the quantum field theory on this region of Scri plus. And this is just the entropy of the Hawking radiation. But then there is another saddle when this splitting surface is non-zero, in which you have these two contributions. Now, the dominant one is the area. This is just this here. The other one is the quantum correction. And in this case, the entropy, when there is a non-trivial splitting surface, is approximately given by the area of this quantum extremal surface, which ends up on the apparent horizon. So which of these two saddles we should take? Well, the dominant one. And which one is the one that dominates? Well, let's see. So the first one is the entropy of the Hawking radiation, so it's going up. This other contribution is just the entropy of the black hole, is the Bekenstein-Hawking entropy, because this quantum extremal surface sits on the apparent horizon. So, well, this is going down. But we are doing a path integral computation. We are using the saddle point approximation. So the dominant one is the minimum of the Chur curves. And so what we find is that up to the page time, the Hawking saddle is the dominant one. And after the page time, the non-trivial island is the saddle that dominates because it's the minimum one. And so you see that in this computation, you recover the page curve. Well, I should stop here, maybe. There are many things I wanted to say, but okay. Yeah, no, maybe we can just stop here and